All right, so 13.5, section 13.5 deals with curl and divergence. Okay, and I'll highlight this. So in this section, we define two operations that can be performed on vector fields and that play a basic role in the applications of vector calculus to fluid flow and electricity and magnetism. Each operation resembles differentiation, but one produces a vector field, whereas the other produces a scalar field. Okay, so let's move forward here and explore this. So the first concept you're going to learn is called the curl. Okay, now I'll show you where the curl is very helpful, but here's the scenario. Okay, so they're being very general, and they're saying, let's suppose we have a three-dimensional vector field, but this could work for a two-dimensional vector field as well. Okay, I mean, a two-dimensional vector field in the XY plane is really like a three-dimensional vector field, just the third component equals 0, right? The R equals 0. So if we have this three-dimensional vector field on R cubed, and the partial derivatives of P, Q, and R all exist, then the curl is defined. The curl of the vector field is given by this definition right here. Let me move this up a little bit. That's the curl. Those are the components of the curl, and you notice they're all like they're combinations of partial derivatives of the components of the vector field. Now, this is difficult for students to remember. Okay, so when students compute the curl, I mean, how many would find this kind of hard to remember? This definition of the curl, which is a vector field, right? The curl of a vector field is itself a vector field. How many think that definition is kind of hard to remember? Okay, Ellie thinks that's a little bit difficult. I agree. So there's a way that you can get the curl of a vector field very nicely. Okay, so it says as an aid to our memory, let's define an operator, a del operator, as what you see there. Now, it's an operator because it operates on a vector field. So think of it, though, as a vector with the components, those partials. But it's just the partial derivative with respect to x, for instance, there, the first component. Well, it's an operator because you don't have like a p in there, but it's going to operate on whatever you put in there. And the same with those other partials. They're going to operate on whatever functions you put in there. Okay, that's called an operator. And you know, again, here, oh well, they actually have it right below here. So the operator has meaning when it operates on a function to produce a gradient. So you know, the del operator, well, if it operates on a function f, you get the gradient vector. Okay? So, all right. So hopefully that makes it a little less abstract for you. So if we think of the del, hello? If we think of the del as a vector with those components, even though that doesn't kind of make sense because, you know, but let's just kind of pretend. Let's think of the del operator as a vector with those components. then if we take the cross product of the del vector with the vector field, then we will actually arrive at the curl of the vector F. Okay, in other words, here, maybe I can highlight it. This cross product between the del operator and the vector field F actually gives you the curl of the vector field, so you don't have to memorize that definition above. And what they're really doing, of course, when you do the curl, you're doing multiplications, right? So like the partial of y times r, it is when you multiply it, you know, it's like the partial derivative of r with respect to y. Even though the partial derivative of r with respect to y is not an operator times a function, it's just, if you kind of think about it, pretend and compute the cross product as if the del operator were a vector, then you end up getting the curl of F. And it's a nice way to remember it. It's a nice way, so actually it's a nice way so you don't have to remember the definition of the curl. So here's the curl of a vector field F. It equals the del operator, a cross product of the del operator and the vector field F. So like, for instance, if we look at computing a curl, let's say, like in example 1, okay, here's your vector field F, and they want you to compute the curl. Well, below, they show the whole process of that. Okay, take a look. Let me know if you have any questions on that. This is example 1. Are there any questions on that? Ian, how do you feel about it? Are you okay with it? Okay. All right. MEH stands for me. I get Malik's good. Okay. Juliana, how about you? You're good with that? Good. Good. Okay. Well, all right. Okay, I see. And MEH is like sort of, but I'll look at it over later. Okay. All right. Well, now, and I'm not going to do all of 13.5 because we're almost out of time here. But let me point something out here. You know, why is this curl? You know, why is this? You know, curl. You know, how's it going to be very helpful for us? Well, one thing is, it turns out that the curl of the gradient field is equal to the zero vector. And so this is a very nice result. So below here, they prove it. It's not hard to prove. But what they do is they say, okay, well, let's take the curl of the gradient. That's going to be del operator crossed with the gradient field. And there they have it. You know, it's in the highlighted box. And if you work it out, you're going to end up getting second partial derivatives. You're going to end up getting second partial derivatives. But by Clairaut's theorem, those second mixed partial derivatives in each component all equal each other. So let me just move this over a little bit. There we go. Yeah, I mean, that's Clairaut's theorem, right? How many remember Clairaut's theorem and how those mixed partials that you see there equal each other? How many remember Clairaut's back from, I believe, section 11.3? I'd like at least maybe one person to say they remember it, but I don't want to force you. Okay, Charles recalls that now. Okay, good, good. So why is this nice? Why is this a nice result that the curl of a gradient is equal to the zero vector? Okay, why is that nice? Well, I'll show you why. This is the reason why. If you have a conservative vector field, remember, a conservative vector field is one in which the vector field can be written as the gradient of some potential function f. But before you search for that potential function, you want to ensure that your vector field is a conservative vector field, right? And you need a criteria to establish that. The criteria that you learned in section 13.3 was for two-dimensional vector fields. We need a criteria for three-dimensional vector fields. Well, it turns out, since a conservative vector field is one such that the gradient of that, the conservative vector field, it turns out, since the gradient of some function would have to equal that vector field, all we need to do is test the vector field out, take its curl, and see if it equals the zero vector. If that's the case, then the vector field f is conservative, because the curl of a gradient of a function is equal, the curl, remember, the curl of a gradient of a function equals zero vector. The curl of a gradient field equals the zero vector. So if the curl of a vector field, if the curl of a vector field is equal to the zero vector, well, then that vector field has to be equal to the gradient of some function. Okay? And so this gives us a way of verifying that a vector field is conservative or not conservative. So, like for instance, in example 2, and I'll sum up here in a few minutes, because thank you for staying a few extra minutes. They say in example 2, show that a vector field f is not conservative. Okay, well, all you do is you find the curl of the vector field, and they did that in example 1, and the curl of the vector field was not equal to the zero vector. So this shows that the curl of the vector field is not equal to the zero vector, and so the vector field f is not conservative. Okay, so determining whether a vector field is conservative or not is extremely important, because we want to be able to apply that fundamental theorem of line integrals when we can. And, you know, the conservative vector fields have very wonderful properties too. Are there any questions on this? Any questions at all? Okay, well, I'll just sum up then with the final theorem here. This theorem right here, theorem 4. Okay, which reiterates what we just talked about. If the curl of a vector field equals a zero vector, then f is a conservative vector field. The vector field f would be a conservative vector field. And on that note, I will stop there. Thank you.